Yes, good morning, students, and nice to meet you again. Today we'll be learning mini batch gradient descent. So recall the previous gradient descent formula in which we update the theta of feature j based on the opposite direction given by the gradient, multiplies with a learning rule rate to make sure that it doesn't undershoot or overshoot. Mostly overshoot, right? So now, what if I told you that this is very inefficient because you're computing the gradient by taking the sum of all the samples, right? So basically, you're taking the overall direction provided by your all samples. So if one of the samples say is a little bit left, you want to go to the right. If another example say that you're a little bit too right, you want to go left. So when you take the summation of that, it will cancel one another, and finally you will get the final direction based on all the samples, which is fine. But the idea is that this is inefficient. What if I tell you that there's a better way, and it's called mini batch gradient descent? And I think you guessed it right. The idea is simply you calculate the gradient based on only a subset of samples, defining by the batch and the index I. So, how do we do this in action? Well, what we can do is we can define the index start as 0, and then we can define the batch size as some number like 16 or 32. And then we can iteratively, every time we update the theta, we can change the number I. So the first time we update the theta, we can set it to 0 to 32, for example. And then the next time we update the theta, we can change it to 33 to 64. And we keep doing it until we exhaust the whole data set. We call this one epoch. So you can see that we can, through just one epoch or through all the data, we can update the theta many, many times compared to this in which you have to look through all the data to just update theta one time. So mini batch is a very important algorithm used throughout all modern and even classic and modern machine learning algorithms and also deep learning algorithms. So make sure that you understand this. So today I have already prepared a code that we have used in the previous session. So you can take a look. It's very similar to what we have already coded in the previous tutorial. And then in today's tutorial, aside from learning mini batch, I will be also making sure that my code is in the class format. I will be implementing early stopping to make sure that I stop if the loss is not improved anymore. I will be introducing the cross-validation, and I will be also introducing and making sure that you know this term called epoch. For cross-validation, I have prepared a picture. It's extremely simple. So the idea is that we have trained our model and we want to test our model on our testing data. We can test on the test set. But what if we want to compare many models? We cannot simply always test on the test set because that is basically you trying to game on the test set and try to beat the test set. In that way, your model will not be generalizing because you always trying to look at whether it performs well on the test set. That is like playing a game. Instead, I want to introduce an idea called cross-validation. In iteration 1, you can imagine chopping the training set into 5 folds. We call this fold. And this is a hyperparameter you can choose. You can chop this into 7 or 10. It depends. But usually people do it 5 or 10. And you can delegate one of the fold as what we call the validation set. So you train your model using this 4-fold, and you validate your model based on fold 1. You get 1 accuracy or 1 performance metric. In the iteration 2, You initialize your model from scratch again, so you don't continue your model again. And then you delegate the second fold as your validation, and you train your model using fourfold, and you validate your model on the second fold, you will get the performance. And you do this 5 times, you will get a very similar performance all the 5 iterations because you initialize the model every time you do the new iteration. So you get very similar, maybe to 5, 5, 5.2, 5.3, something like this. And you take an average, you will find that this average gives you good average of whether how well your model will perform on the test set because it's a good average, right, of unseen data, right? So that is a very good way. Cross-validation allows you to compare different models, different hyperparameters without looking at the test set. So we will be also implementing this in from scratch. And lastly, lastly, we're going to introduce this for. Please making sure that all of these things I will teach you can be easily done in sklearn. But in my class, my main purpose is to teach you the mechanism. So you will be learning from scratch. So, but when you are doing in industry, you would want to simply use sklearn and all the tools available in sklearn. So let's start. So as promised, I will be creating a class. All right, so let us begin. We're going to do class, let's call this linear regression. And then I'm going to just put object, right? So this is a very basic class initialization in Python. And then we're going to say in the init function, it's going to be self, which is for those who are familiar in programming, self is basically like a this in Java. And then we're going to do, we're going to accept learning rate, number of epochs, and we're going to default it into 500, and the batch size to be 50. And the method could be, we can have a batch and mini, okay? But batch is basically using everything, and the CV is a k-fold. All right, and to implement this, we will be using the help of k-fold, which simply divide the data for us, right? So this is very nice. And so to make sure that we have this k-fold, we should say that k-fold equal to k-fold and splits equal to 5, right? So let us take a look at this. Okay, I think this should be a space. So let's take a look at this k-fold, right? Because not everyone is familiar with this k-fold, right? So this is the example, right? So if you put an array of x and y, and you say that k-fold n split equal to 2, right? And you want to split this array, right? So what does it do? Well, this is, you first need to understand this example, right? This is a first sample, second sample, third sample, fourth sample, and this is a feature 1, feature 2 of each of the sample, right? So once you do that, you can see that for 0, the index will be 2 and 3. So these 2 samples become the training data set, and then the testing will be these 2 samples. But in for 1, it will change, right? 0 and 1 will be the training set, and then the testing set will be this one instead. So why do we only have 2-fold here? Well, because you specify the n split equal to 2, right? So you will always have only 2-fold here. So this is just for your example, what does this k-fold does? All right. So hopefully you understand. If you don't, you can keep reading and eventually you will get it. All right. So so let us making sure that we all have this, right? So equal to LR and self.num epochs equal to num epochs, right? And I want to measure my things looks very nice. Self.ps equal to ps and self.method equal to method and self.cv equal to cv. All right. So by doing this self thing, all the method below will be able to access this variable, right? This is a very basic thing. I will be also implementing the MSE function. So I will do this quickly because this is a pretty straightforward. So the MSE is basically, so I know that I need to divide it by the total sample size. So I know that that is y dot shape 0. By the way, recall that the shape is simply m, right? Which is basically in which m equal to the number of samples. Yes, and in our class, n refer if we have this term n, it means the number of features. Yep. So I know that I will do that. And here I'm just simply say that y predict minus y true, and then square them, right? And then finally, okay, maybe I don't need this bracket. And then I will say, once I square them, I will be summing them, right? So this is a very simple implementation of this MSE. What else will be coding first before we do this fit method, right? Which is by the way, you can see that I'm using the same term as sklearn, so that you can get an idea that when you call sklearn fit, what does it really do, right? But I think I will do the predict function first because it's pretty easy. So predict self x, right? Given the whatever the x, I will simply self theta, right? And this is simply saying that m comma n, right? Dot with theta, which is the n comma, right? So we know that this is the shape of the x, which is m comma n, and theta is n, right? If you don't remember this, just go back to my previous tutorial and you'll get it, right? And the shape and the resulting shape is this will cancel this one and you'll get m, right? Which is, you know that this is correct, right? Because this is basically the shape of y, right? And you know that by doing this, you get y, which is this. So you know that you're correct. I will also write a function for getting the data. So I will get a function called this. The reason why I use this name is simply because sklearn also do this. And underscore is just a good practice in Python, saying that you don't usually allow the user to use this, right? It's mostly for internal use case. So that's why you put the underscore. So I know that theta, and I'm gonna put 1 here because here recall that when I do the adding intercepts, I add in front, right? So I know that whatever that is from 1 is not the intercept. And likewise, if I want to get the intercept of the bias, I would just do return self dot theta 0, right? Okay, great. So we got this small functions. Let us punch that. I don't think there's any problem. The next one we want is to write this function called train, all right? And this is not the same as fit, right? Because in fit, you have to do cross-validation, training, cross-validation, and then locking metrics and checking whether it's early stopping. So you can say that training is inside the fit method, right? So let us write this function, and I'm gonna call this train, and then I'm gonna say, what if I got this x and y, and I want to learn the patterns of this pair of data set, right? Please note that in fit, we're gonna put this as X train, right? But in the function, we don't need to say that this is train or test, right? So recall that there's a 3 steps in training, right? So first we predict, and then we calculate the gradient, right? And then we update the t, right? And because this is a function, we may want to return something. Great. So let us try to do this, right? So y hat equal to self dot predict. We already have this function, right? And then call x, right? And then that's it, right? And for the gradient, gradient is equal to 1 over m multiply with x dot t at y hat minus y. All right. So this is basically the formula that is based on the previous tutorial again. So nothing new, but I think we need this m, right? So m is equal to x dot shape 0. By the way, when we come in, the shape of x is m comma n, and the shape of y is n. Right? By the way, when you do this, you will eventually get a hang that x is mn and y is n. All right, and n is basically number of features. Sorry, it's m. Right. You will get a hang that n is a number of features and m is a sample size. All right. So eventually so you should do a little bit of exercise, right? Whether this one makes sense, right? So y hat minus y is basically m comma minus m, right? So this will, because it's just a minus, the shape will be m, right? So this will be m, right? So this is done. So now you dot with x dot t, right? So x dot t is simply n comma n, because you transpose. You dot with this one. This one will cancel out with this one. You will get n comma, right? And multiplying this won't change the fact that this is a shape. And you please check, because you want to update the gradient with the theta, and this is exactly the shape of theta, right? If you recall, right? So then it seems like you are doing a correct job. Finally, you want to do the update. So we just say self.theta equal to self.theta minus self.loading rate multiplies with gradient. And then actually you don't need to return anything, because automatically, because self.theta is updated, the whole class knows itself, right? But what I just want to do is to return MSE, just so that it looks very nice on my fit method, right? So I think that's it for almost all the method. Now we just need to write this fit, and then we are good to go, right? So let us begin. Before anything, let me just shift enter, and now we do this fit method. So fit self, and normally in sklearn you put in the x train and y train. So let us think what we need to do here. So there's a lot of things we need to do here. We need to create a list of K4 scores, right? For a list for keeping K4 scores. We need to have a variable to know our loss is not improving anymore. Right? And then we just do the cross-validation thing right here. And yeah, I think that should be it, right? So let us try to do this, and we're gonna be slow, because it could be not easy for some of the new students. So we're gonna say is a list, right? So this is gonna be basically a list to keep the scores of each of the model, and we're gonna say self.validation loss O equal to np.infinity. So basically the idea is that because this is the old loss and this is very big, it will improve one time, and it will keep improving when the new loss is not lower than the old loss, right? Then so basically the new loss is not less than the old loss, then we stop, right? By how much? What we can define something like if it's not smaller than 0.01 and or by any numbers, right? This number we call usually tolerance, or in short, we call this tolerance. Yeah. All right, so in the cross validation, well, what we can do is we can do something like this, right? For fold, comma, train index and validation index, right? Which is provided by this CV split, which we already looked at the code, right? And we imagine that X train is M comma N and Y train is M. So what we can do is we can say that X cross train equal to X train index and Y cross train equal to Y train index. So based on this split, we're gonna use only this subset of X train data, and we call this is our training set. And we're gonna also assign the validation. Again, you don't have to do this in industry, but what I'm trying to teach you is it's basically the underlying mechanisms. Validation index, right? Great. So you now have all the data sets ready for you to train your model using these two pairs of data set, and then test your data model on this, right? And finally, you can test your testing set later on after you train everything, right? So remember, in cross validations, you only deal with the training set, right? So now we can say that for epoch in range self.non-epochs. So for every time you do run an epoch, you want to use the whole data set here, right? For one fold is called epoch, right? So epoch, the idea is basically you exhaust the whole training set one time, it's called one epoch. So in the so let us do permutation a little bit, right? So let's just shuffle the data a little bit so that the order does not impact our model. Usually it does not impact, but it's good that we do this. So we're going to say perm equal to np.random the permutation, and how many permutation I want. I mean, how do you want this permutation? So I just say send the sample size of this. So for those who wonder what does this return, perm will be something like if this is 200, it will be something like 250, 67, like basically a list of indexes from 1 to 200 and then permuted. So it's basically a list, right? That is permuted 200 until 200, right? So you take 1 to 200 and then you permute it and you get this list, right? So that is ideal. And then we're gonna say X cross train equal to X cross train perm. And then Y cross train equal to Y. A lot of students love to ask me, should you always do this permutation? I think yes, it does not give you any harm. And also, but some students also ask me what sometimes they don't need to permit and the performance is good. Well, simply because the data set may be the people who prepare the data for you already somehow randomly permute the data for you already, right? So in that case, that is the reason why it looks so good, right? So make sure that you understand why it's that. So now what we're going to do is if self.method equal to mini, we're going to do something, right? But otherwise, if the method is batch, right, which is well, we're just going to train with the whole thing, right? Train equal to x plus, right? And y method train equal to y plus train. So please don't confuse between cross validation and mini batch, right? It's totally not related. Cross validation is basically the idea of splitting your training set into validation and training so that you can estimate how much loss you have, right, in the testing set. But for mini batch is basically the idea of when you compute the gradient, you only take a subset of training, right? So so the idea of mini batch and cross validation is not the same, right? By the way, this is the for cross validation, right? But for mini batch, the code will be here, all right? So if it's a batch, we just simply use all the data, right? But if it's a mini batch, what we're gonna do is the following, right? But before, let me finish the batch. So I'm gonna say that train loss equal to self.train, which we already write this function, x method train, y method train, right? But for mini batch, again, is totally different from cross validation. It's not related, right? So in mini batch, what we're going to do is for batch index in range 0 x cross train dot shape 0 cell dot batch size. Right. What I'm going to do is x method train equal to x cross train batch index into batch index plus cell dot batch size, right? And then until the end, right? So you start here, right? If it's beginning at 0, it will be 0, right? 0 until the required batch size. Which if the batch size is 32, so this will be 0 until 32, right? But for the number of features, you would just use everything, right? So this is again, remember that for n, for x, this is n and this is n, right? So, and then similarly for y method train, y cross train, batch index plus cell down batch size, right? So you can see that there's no relationship between mini batch and cross validation. The idea of cross validation is that you try to split your training set so that you can have training set and validation set and you can estimate. But for mini batch, the idea is that using only this cross cross validation set, you do this and you update your theta or using this subset. Right. So this is very important that you understand the difference between the cross validation and mini batch. Hopefully you don't get confused. But if you do, well, you just simply watch my video again, or maybe look at the code closely, and you will eventually understand what is the purpose of cross validation and the purpose of mini batch. All right. So now we are quite good, right? So we for each of the epoch, what we do is if it's a mini batch, we're gonna update many times. we can update our model many times, right? But if this is a batch, we just use the whole thing and we update just one time, right? And then after one epoch, what we're gonna do is, in fact, what we're gonna do is now we can calculate the metrics, right? And making sure that we have all this number. So so finally, after for each of the epoch, what we're gonna do is we're gonna do y at 12, so this is self.predict x cross 12, right? So what I'm trying to do, well, after I update my model, now I'm gonna take the validation set, which is set here, and then I want to predict it, right? Based on the model. Here, I'm updating my model many times. Here, I'm only updating my model one time, right? And then what I can do is while loss new equal to self.mse y cross val and y can val, right? So here I'm just simply calculating the loss, right? And then finally, I want to implement the early stopping. That is if np.r close val loss new and self.val loss old, right? If they are very close, right, then you should not continue training. You should just stop and then forget about this, right? Otherwise, you want to old equal to val loss new, all right? All right, so now lastly, what you can do is just give me 1 second and make sure that my code is correct. All right, so I think I'm correct now. And finally, what we can do is once we finish all the epochs, what we can do is a self.k4 scores that append val loss new, right? So we can get that after one of the four, right? We can get the score, right? And then we can say that print bold, and val loss new. All right, great. So it would just print 0, this is a loss, 1, this is a loss, right? So let us take a look again, right? What we are trying to do here. It's a little bit complicated, right? So we have a list of K4 scores. We have this validation variable to keep track that the loss is not whether it's improving. And then for each of the 4, we split the training set differently. And in that difference, we set them into the training set and the validation set. And then for number of epochs, we're gonna first shuffle them. And if this is a mini batch, we're gonna update our parameters using a subset of samples to update our theta. And we do this until we use all the data set. If this is a batch gradient descent, well, it's simple. We just take the data set and then we just train it, right? Finally, after each of the epoch, we predict the cross validation and we keep track of the loss, right? And if the loss is not improving, we just simply break out from this epoch. Otherwise, we're gonna keep the new loss. Finally, after each of the four, we calculate the K4 scores and then we print it out so that we know what we're doing, right? So hopefully this is not overwhelming. Please pause the video if you think that is a little bit slightly difficult, but I'm gonna just run this and then now I'm gonna close this, right? So what we're gonna do now is, okay, give 1 second. Interrupts, testing, right? Now I'm going to close this. Now I think it's time that we can try to test our data set on our data, right? So how do we use our class that we just defined? Well, it's actually very easy. We just say model equal to linear regression method equal to mini method equal to mini, and then learning rate equal to actually I don't need this thank you method equal to mini, and then the learning rate equal to 0.01, right? So expected parameter name. Okay, give me 1 second. Right, so it seems like there's no problem, right? And then what we can do is, so let me just take a look at the parameters I need to send it, right? So I'm just going to copy this one and close this. And I want to make sure that, so the init function will define what I need to put in, right? So learning rate is anyway, that one anyway. So I'm just going to delete. Method I need to change to mini batch. Num epoch I'm fine. CV I'm fine. So that should be it, right? So yes. So now I got the model defined for me. Now what I can do is model.fed train and y train, and this data set is defined in the previous code. So I can do this, and hopefully there's no error. And I already have some problem. Has no attribute batch size. So obviously I did not define this term called batch size. So let me do it real quickly. Start. And here it should be BS, right? Okay, give 1 second. Okay, and let me just search whether I have this term. Okay, great. So I think that should be it. And so I'm gonna run this code one more time. All right, so now I think I can close this and then let me try again. All right, so now I have one more problem. Too many indexes. So y cross train should not have this column because y is just an m, right? So it does not have that. So let me just quickly fix that. Okay. So hopefully things will work now. All right, so now I have one more problem. Y method train. Okay, so this is line 50. I have one more, I think. So I have here, and okay, this is strange. Maybe I should run this again and run this again. Okay, great. So now I have done here. Now linear regression has no theta, right? So let me make sure that I have this variable theta accordingly, right? 1 second. So I never defined this, right? All right. So what we can do here, actually, there's something I forgot here, right? So I should define cell.theta equal to np.zeros x cross train.shape. So x is m comma n, right? And theta should be n, so that should be 1. Right? Okay, great. So hopefully this should be fine. Great. So I think we got the fit method. So let me first close this, and then we can now let's look at the numbers, right? So you can see that we got this loss, and that they are very similar across four, which is a good sign that our models tends to be around here, right? And you can see that by using this way, you can estimate that if you apply this model to the testing set, it will be likely the average of between here, right? So now, in fact, why don't we just try to check the real right? And then we can now get the MSE. Yes. And finally, we can simply print right? And trust me, if there's nothing wrong, this number will be something around here, right? Because this is it's validated, right, in the training set with 5 folds, right? And if you take the average, it should give a good number estimate on the test. All right, and okay, great. Okay, great. So you can see that this number is roughly this. So remember that remember that cross-validation is the purpose of cross-validation is so that you can test your model and compare different hyperparameters, compare models without actually taking a look at the testing set. But at the same time, you can estimate correctly. But for the mini batch, the purpose is to make sure that you do not use all the samples to calculate the gradient for updating the theta. Instead, you only use a subset, right, to update the theta. And once you use the whole, you iterate all the batch, we call this one epoch, right? So those are the things that you need to remember. All right. So I think that's it for the mini batch. And hopefully you can review again, pause my video if there's anything confusing, and see you next time. Bye-bye.